Imagine the fastest thing in the universe. Naturally, your first thought is probably light. Light travels at about 300,000 kilometers per second, and according to Einstein's special relativity, nothing can surpass it. It's the ultimate speed limit woven into the very fabric of physics. Yet, when we study gravity, the force that keeps planets in orbit, pulls apples from trees, and shapes galaxies, it behaves in ways that seem almost instantaneous. While light is fast and measurable, gravity's influence appears to reach across vast distances with astonishing immediacy. This raises an unsettling question. Could gravity, in some sense, move faster than light? To explore this, we need to reconsider what we mean by speed. Speed in everyday life is simple. It's how quickly a car travels from one city to another, or how fast a ball flies through the air. But when we talk about forces like gravity, speed becomes more abstract. Gravity is not a physical particle moving through space like a bullet. Instead, it is the curvature of spacetime caused by mass. Objects respond to that curvature. When the sun's mass bends the fabric of space, Earth follows a curved path, which we perceive as orbiting. The influence is encoded in the structure of spacetime itself, not transmitted through a medium in the way sound travels through air or light moves through space. Einstein's general relativity predicts that changes in gravitational fields propagate at the speed of light. If the sun were to suddenly vanish, the Earth would continue orbiting along the same trajectory for roughly 8 minutes. The time it takes light to travel from the sun to Earth before we noticed any difference. This principle ensures that relativity's cosmic speed limit remains intact. Yet when we examine real-world interactions, the story becomes more complicated. Observations of planetary orbits, binary star systems, and the motion of galaxies suggest that gravity exerts its influence almost immediately. The planets respond in ways that seem faster than light would allow. This apparent contradiction is partly because gravity operates on a scale and in a manner that defies everyday intuition. In daily life, cause and effect feel sequential. One event leads to another, and we can track the progression along a timeline. Gravity, however, is not a sequential messenger. It is woven into the geometry of the universe. The static gravitational pull that keeps planets in orbit acts as if the influence is instantaneously present. Unlike light, which must travel across space to convey information, gravity is the property of space-time itself, and space-time reacts collectively to changes in mass and energy. Our struggle to grasp this is understandable. Human intuition evolved in a world where signals move through mediums. Sound travels through air, objects collide, light reflects from surfaces. We are trained to think in terms of propagation, distance, and delay. Gravity, on cosmic scales, doesn't fit these models. It bends space, connects distant objects, and orchestrates motion without a conventional signal traveling between them in the usual sense. This creates a tension between theory and observations. Einstein's equations tell us that gravitational waves move at light speed, yet the static field appears to operate with astonishing immediacy. Understanding gravity's behavior forces us to rethink what speed truly means. We are accustomed to measuring it in units of distance over time, yet gravity challenges this concept. Its influence is not a particle or wave that traverses space in a classical sense, but an intrinsic feature of the universe's geometry. Light travels, photons have speed, and we can detect them. Gravity shapes the very stage on which those photons move. It is an invisible, almost mystical force that binds the cosmos together in ways that our common understanding of speed cannot fully capture. By examining the speed of gravity compared to light, we confront the limits of intuition. Light, fast as it is, travels along the fabric of space-time, while gravity defines that fabric itself. This distinction is subtle but profound. It reveals that the universe operates according to rules that are often counterintuitive, where forces, fields, and space-time interact in ways that challenge the simplest ideas of cause, effect, and motion. The deeper we look, the stranger the universe appears, and gravity stands as one of its most mysterious and elegant secrets. To understand why gravity appears to act faster than light, we need to explore its dual nature. The static field that holds celestial bodies in orbit and the dynamic waves that propagate through space-time. The static component of gravity is what keeps planets revolving around stars and moons circling planets. It appears to act instantly, binding distant objects across the vast emptiness of space. In contrast, gravitational waves are ripples in the fabric of space-time. generated when massive objects accelerate, such as in the collision of black holes or neutron stars. These waves travel at the speed of light, carrying energy across the universe. Both aspects coexist, but our intuition struggles to reconcile them because they behave so differently. Imagine a massive star suddenly shifting its position. The surrounding spacetime would adjust to this change. For distant objects, the static gravitational influence would maintain their motion as if the shift were instantaneous, while any ripples in spacetime, the gravitational waves, would propagate outward at light speed. Observationally, the planets in our solar system do not experience sudden changes in orbit due to distant stellar movements. This gives the impression that gravity is instantaneous. However, when we detect merging black holes through gravitational waves, we measure their propagation precisely at light speed, confirming Einstein's prediction. The paradox arises because our minds interpret the static influence as faster than light action, while the dynamic component strictly obeys relativistic limits. This behavior is deeply tied to how mass curves space. Gravity is not a force transmitted across a distance like a moving particle. It is the shape of space itself. When a massive object exists, it creates a dip or curvature in spacetime. Other objects moving nearby naturally follow paths dictated by this curvature. The changes in mass distribution, however, produce ripples that spread outward at light speed. The static curvature does not travel. It defines the geometry in which objects move. It is like a stretched trampoline. The dip caused by a heavy ball immediately influences the motion of smaller balls on the surface. If you suddenly adjust the ball, the entire trampoline shape shifts, guiding the smaller balls along new paths. The effect is immediate within the context of the surface, though any real ripple in the fabric of the trampoline takes time to propagate. Gravity behaves similarly on cosmic scales. Binary star systems provide a natural laboratory for studying this phenomenon. In these systems, two massive stars orbit one another, emitting gravitational waves as they accelerate. By precisely measuring the orbital decay of these stars, scientists have confirmed that energy is radiated away at the speed of light, matching the predictions of general relativity. Yet the stars' orbits remain consistent with the idea that the gravitational influence is effectively immediate, keeping the system stable over millions of years. This duality, apparent instantaneous action versus finite speed waves, is at the heart of the apparent faster than light paradox. Human intuition struggles because we naturally think in terms of signals moving through space, like a bullet or a sound wave. Gravity does not fit this framework. Its influence is encoded in the very geometry of spacetime, making it both immediate in its static form and bound by light speed limits in its dynamic form. The universe is vast, and the distances involved are enormous, yet gravity ensures stability and cohesion, holding galaxies, solar systems, and clusters together in ways that seem instantaneous to our perception. Understanding this dual behavior is key to reconciling the apparent speed of gravity with the constraints of relativity, and reveals just how different cosmic scale physics is from our everyday experience. Gravity challenges our perception of causality and distance. Its static influence suggests a universe more interconnected than intuition allows, while its dynamic waves confirm the ultimate speed limit set by light. The interplay between these aspects forces us to rethink what we mean by speed, influence, and action at a distance. In studying gravity, we see that the universe operates on principles that blend immediacy with constraints, creating a cosmos that is stable, yet profoundly counterintuitive. This is why the faster than light mystery persists. It is not a violation of physics, but a reflection of the subtle and intricate nature of spacetime itself. To grasp why gravity seems faster than light, we need to explore the distinction between how humans perceive motion and how the universe actually operates. In our daily experience, speed is always about something moving from one point to another. A car drives from one city to the next, a ball flies across a field, or sound waves travel through air. These examples all involve a signal or object traversing a medium over time. We naturally assume that any influence, any action, must propagate similarly. Gravity, however, does not behave like a conventional signal. It is not an object moving through space. Instead, it is the shape of space itself. Mass curves spacetime, and this curvature dictates how other masses move. When we try to assign a speed to this influence, it appears instantaneous in ways that challenge our everyday notions. The static aspect of gravity is key. When we observe planetary orbits, the moon circling Earth or Earth orbiting the sun, the gravitational influence seems to be acting immediately. If the sun were displaced, the Earth's orbit would adjust as though the change had already reached it, rather than waiting 8 minutes for the light to arrive. This immediacy is not a failure of physics, but a consequence of the fact that the static gravitational field is tied to the mass's position in spacetime. It is not propagating. In the conventional sense, it defines the geometry through which objects move. This distinction between the propagation of changes and the influence of the existing field is subtle, yet crucial for understanding why gravity feels faster than light. Gravitational waves, in contrast, are dynamic disturbances in spacetime caused by accelerating masses, such as colliding black holes or merging neutron stars. These waves do travel at light speed, carrying energy across the cosmos. When scientists detected gravitational waves from merging black holes in 2015, they confirmed this prediction with extraordinary precision. These waves provide a direct measurement of gravity's speed in its dynamic form. Yet the static field, responsible for maintaining orbits and the structure of galaxies, appears to act as though it were instantaneous. This dual behavior can seem paradoxical, but it aligns with general relativity. One part of gravity maintains the geometry of spacetime, while another part, the waves, transmits changes at light speed. Thought experiments help clarify this. Imagine a distant star connected by an invisible string of gravity to another star. If the first star suddenly moves, the orbit of the second star adjusts as if the change were immediate. The dynamic waves of spacetime curvature ripple outward at light speed, but the overall geometry that defines the orbit responds in a way that preserves stability. This is analogous to stretching a rubber sheet with a heavy ball. The sheet's curvature dictates the motion of smaller balls, and adjustments propagate, but the overall dip in the sheet is what guides the motion instantaneously. Gravity operates on a scale that makes our human intuitions about signal propagation inadequate. Our brains struggle because we are conditioned to expect time delays and sequential effects. Light is a signal traveling from one point to another, measurable and finite. Gravity, however, is woven into the framework of reality. Its influence is both immediate in the sense of maintaining cosmic structure and finite in the sense of propagating disturbances through waves. Recognizing this distinction dissolves the apparent paradox. Gravity does not violate relativity. It challenges our instinctive assumptions about causality, speed, and influence. The realization is profound. Gravity binds the universe together, ensuring stability across billions of light years. While its waves obey the universal speed limit, it operates on a deeper level than light, connecting matter through the very fabric of spacetime. This dual nature forces us to expand our understanding of what it means for something to have speed, to exert influence, and to shape the cosmos. Gravity, in its mysterious and elegant way, reveals that the universe is far more interconnected and subtle than our everyday experiences suggest. It teaches us that apparent, instantaneous, action and finite speed propagation can coexist, reflecting a cosmos that is both stable and dynamic, immediate and constrained, simple in principle, yet astonishingly complex in behavior. To dive deeper into the mystery of gravity versus light, we must examine how our understanding of cause and effect is challenged by the cosmos. In everyday life, causes produce effects sequentially. A stone thrown into a pond creates ripples that travel outward at a finite speed. We intuitively expect that all influences, whether forces or signals, behave similarly. Gravity, however, defies this expectation. Its static component, the force that holds planets, moons, and galaxies in their orbits, acts as if it is already present everywhere. There is no delay that we can measure in the orbital motion of celestial bodies. This apparent immediacy is what makes gravity seem faster than light, even though the dynamic component of gravity, gravitational waves, still obeys the speed limit set by relativity. Understanding this requires a closer look at the geometry of spacetime. In Einstein's general relativity, mass and energy curve spacetime, and objects follow the paths dictated by this curvature. When a massive object is present, it warps the fabric of space around it. Other objects do not feel a force traveling toward them. They simply move along the curved paths that exist in the geometry. The curvature is not a message traveling across space. It is the structure of space itself. A distant planet in orbit around its star is responding to the shape of spacetime created by the star's mass. If the star were moved slightly, the planet would follow a path determined by the new curvature. The apparent instantaneous effect is a natural consequence of how space itself is shaped by mass. Gravitational waves are a separate phenomenon. They occur when massive objects accelerate or collide, producing ripples that propagate through spacetime at the speed of light. These waves were directly detected in 2015 from colliding black holes, confirming Einstein's prediction. The key is that gravitational waves are not the static force that holds systems in equilibrium. They are disturbances that travel outward, carrying energy. The static field that defines the overall shape of orbits is effectively frozen into the geometry of space, while changes in the distribution of mass propagate as waves. This duality explains why gravity can appear faster than light while still remaining consistent with relativity. Human intuition struggles because we are used to thinking in terms of objects moving through space over time. Forces are normally transmitted by particles or signals traveling from one point to another. Gravity, by contrast, is encoded in the structure of space itself. Its influence is inherent to the geometry, not transmitted as a conventional signal. This makes the static field seem instantaneous, while dynamic changes, expressed as gravitational waves, propagate at finite speed. Our minds are not naturally equipped to conceptualize forces that are both immediate and constrained, because such behavior has no analogy in daily experience. Celestial mechanics offers concrete examples. The moon orbits Earth in a stable path, influenced by the combined curvature of spacetime created by Earth, the Sun, and other planets. This stability is maintained without measurable delay. Meanwhile, gravitational waves from distant cosmic events traverse space at light speed, eventually reaching Earth, where they are detectable by sensitive instruments. The coexistence of these two behaviors, apparent immediacy and finite speed propagation, is one of the universe's most counterintuitive yet elegant features. This understanding reshapes our conception of speed and influence. Gravity does not violate Einstein's principles, it operates within them. But in a manner that transcends simple intuition, it shows that the universe is interconnected at a level far deeper than what we perceive in everyday life. The force that binds planets, stars, and galaxies is both immediate and constrained, demonstrating a cosmos that is stable, coherent, and yet astonishingly subtle. Gravity teaches us that speed, causality, and influence are not always what they seem, and that the universe operates on principles far more intricate than our human experience allows us to imagine. To further explore the speed of gravity, it helps to examine the practical implications of its dual behavior across the cosmos. Gravity is the invisible glue that holds the universe together, from the smallest planets to the largest clusters of galaxies. Its influence is so pervasive that entire cosmic structures rely on it for stability. Without gravity acting effectively instantaneously in the static sense, the delicate balance of orbital systems and galactic formations could not exist. Planets would drift unpredictably, moons could escape, and galaxies would fail to cohere. This apparent immediacy allows the cosmos to maintain order, while dynamic changes, in the form of gravitational waves, ripple outward at light speed. The coexistence of these aspects underlines how subtly the universe balances immediacy and constraint. Consider a binary star system where two massive stars orbit each other. The star's motion produces gravitational waves that radiate energy, causing a gradual decay of their orbit. These waves travel at the speed of light, confirming Einstein's predictions. Yet, the stars themselves respond to each other's gravitational pull in a way that appears instantaneous. The static field maintains orbital stability, while the waves carry information about dynamic changes. Observations of such systems show remarkable consistency between theory and measurement. This demonstrates that while the static influence of gravity seems faster than light, the dynamic waves, which transmit changes, remain bound by relativistic limits. This dual nature is not a contradiction, but a subtle feature of spacetime itself. The trampoline analogy helps illustrate this. Place a heavy ball on a stretched trampoline. The dip in the surface represents the curvature of spacetime caused by mass. Roll smaller balls near the heavy ball, and they naturally move toward it, guided by the curvature. If you lift the heavy ball slightly, the shape of the trampoline changes. The smaller balls respond to the curvature already present, while ripples from the adjustment propagate outward at finite speed. Gravity behaves in a similar manner. The static curvature of spacetime guides motion across cosmic distances immediately, while dynamic disturbances move as waves at light speed. Our intuition struggles with this because we are accustomed to thinking only in terms of moving objects or signals. Human perception adds to the confusion. We evolved in a world where cause and effect is sequential and distances are small compared to cosmic scales. On Earth, forces propagate through matter or radiation, and we are used to seeing delays. Gravity operates on a scale where these delays are negligible for the static field, giving the impression of instantaneous action. The dynamic component, however, shows that changes are still constrained by the speed of light. Our brains are not designed to naturally grasp interactions on such a scale, which is why the speed of gravity seems paradoxical. Gravitational waves, recently observed from colliding black holes and neutron stars, provide the experimental confirmation that gravity's dynamic changes propagate at light speed. Yet the stability of orbits across millions of light years suggests that the static field is inherently woven into the geometry of spacetime. This combination of immediacy and limitation is fundamental to the universe's structure. Gravity ensures cohesion, preserves cosmic order, and allows systems to function predictably over billions of years. At the same time, it transmits new information at finite speed, respecting the universal speed limit. Ultimately, the universe demonstrates a remarkable balance. Gravity appears faster than light in one sense, yet obeys fundamental relativistic rules in another. This dual behavior highlights the complexity of the cosmos and challenges simple notions of speed, distance, and causality. Understanding this helps us see the universe not as a collection of objects interacting in linear sequences, but as a dynamic, interconnected structure. Gravity is both immediate and constrained, simple in concept but subtle in execution. Its behavior expands our understanding of how the cosmos functions, revealing a reality more intricate and interconnected than our everyday experience allows. Gravity's behavior forces us to reconsider fundamental concepts like speed, causality, and influence. In everyday life, we are accustomed to signals and forces moving through space over time. A ball rolls, a sound travels, light shines, and everything occurs in sequence. Speed is measured as distance over time. Gravity, however, does not fit this framework neatly. Its influence is encoded in the curvature of spacetime, meaning it is both present and active across vast distances simultaneously. When an object moves, the static curvature of spacetime that governs motion already exists, guiding other objects immediately. Dynamic changes, such as those from accelerating masses, propagate as gravitational waves at the speed of light. This duality, static immediacy alongside finite speed waves, is difficult to grasp but perfectly consistent with the laws of physics. To understand this, consider the nature of spacetime itself. Einstein showed that mass and energy tell spacetime how to curve, and spacetime tells matter how to move. The static component of gravity, the curvature of space around a mass, is a feature of the geometry itself. It is not traveling from one point to another. It exists inherently in the space surrounding the mass. Objects moving through this curvature respond immediately to its shape. The dynamic component, gravitational waves, carries information about changes in mass energy distributions. These waves travel outward at light speed, ensuring that changes in mass do not instantaneously alter distant objects in a way that violates relativity. The coexistence of these aspects is subtle but critical. Imagine a massive planet with a moon orbiting it. The moon's motion is governed by the curvature of spacetime created by the planet. If the planet were to move slightly, the moon's orbit adjusts as dictated by the existing curvature. Meanwhile, the disturbance in spacetime caused by the planet's movement propagates outward as a gravitational wave at light speed. The static geometry maintains immediate guidance, while the wave communicates dynamic information. Observations of planetary systems and binary stars confirm this behavior. The duality resolves the apparent paradox of gravity acting faster than light. The static influence seems instantaneous, but changes propagate in accordance with relativity. Our intuition struggles with this because we evolved in a world dominated by localized, sequential events. We see one thing happen, then another, and expect delays between cause and effect. Gravity operates on a scale far beyond terrestrial experience. Its effects extend across billions of kilometers and even light years, shaping galaxies and clusters without perceptible delay in the static sense. Meanwhile, Gravitational waves communicate changes at light speed, maintaining causal consistency in the universe. Understanding this requires abandoning the notion that speed, in the usual sense, can fully describe gravitational influence. Gravitational waves, recently observed with instruments like LIGO and Virgo, provide direct evidence that dynamic changes in gravity propagate at light speed. Meanwhile, the static gravitational fields that govern orbital mechanics behave as though influence is already present, enabling stability across vast scales. This dual nature allows the universe to remain orderly and predictable, from the motion of moons to the rotation of galaxies, while still adhering to fundamental physical laws. The implications are profound. Gravity challenges our perception of speed and influence, showing that the universe operates on principles beyond everyday intuition. It reveals a cosmos that is interconnected at the deepest level, where the geometry of space itself guides motion instantaneously, and waves propagate changes at the ultimate cosmic speed. Gravity demonstrates that immediacy and limitation coexist naturally, creating a universe that is stable, dynamic, and profoundly interconnected. Recognizing this duality allows us to see that the apparent faster than light nature of gravity is not a contradiction, but a window into the deeper structure of reality, a glimpse of the intricate architecture that governs the cosmos itself.